Okay, so I think we need to learn to find the E field if we already know the scalar V field. Okay, so that's kind of what we're trying to accomplish. And so you can take any arrangement that we had last time. So Mr. Shore is just kind of looking back through his notes, and I'm going to go ahead and pick, it's actually the same example the book does. They started with the charged disk when they talked about this subject. So let me find the charged disk equation real quick. Okay, so you might remember that the V for a charged disk is 2k sigma times square root of z squared plus r squared minus z. And this is the potential, the scalar potential experienced at any point z units above or below the very center of the charged disk. So it was a very symmetric kind of thing. But if you kind of go up or down, you have different z's. You plug those z's into the formula both here and here, and out pops a number. That's your potential, right? Keep in mind that the R, the capital R you see here, is the fixed radius of the original disk. So it's not a variable at all, actually. Capital R is not a variable. Okay? All right. The K, of course, is a constant. The sigma is a constant, just like the R is a constant. All right, so technically what you're supposed to do is you're supposed to get the E field, you have to actually do a couple steps. The first thing you have to do is you have to derive the V field with respect to every possible spatial dimension. So you have to ddx it, you have to ddy it, you have to ddz it, every dimension. This produces 3 slopes, 1 in each dimension, okay? Or if you're using a different system, let's say you're interested in cylindrical coordinates and you want to travel this way or radially away from a point, you could use a different system like cylindrical. So you can actually use spherical, or you can use cylindrical, or you can use Cartesian. It's kind of up to you. Your results will all look different and they all have different meanings. Okay, for our purposes, I think it'd be a little too complicated to even leave the z-axis. So we're only going to go straight up or straight down, traveling along this. Also, our formula, our V formula, is only valid if we stay on this line. So even though you're supposed to derive in every possible dimension and then put a vector, like a little hat on each one, and keep them all separate, we only have one dimension here that we can even travel in. So I'm only going to do a partial derivative with respect to z. Only. So you might want to involve x and y, but they aren't interesting to us, and I'm not sure our V formula is even valid. We only have 1 degree of freedom here for this problem. Okay, and then there's a negative that pops up automatically and a direction that pops up. Okay? The negative comes from the idea that the physicists chose field lines to come out of positive point charges and terminate on negative point charges. This causes an unfortunate negative relationship between the derivative of scalar functions in electrostatics and their vector counterparts. So that's unfortunate. That negative is just there to stay. We can't do anything about that. The z hat comes from the fact that we need E to eventually be a vector. So we have to assign some kind of a hat to it. And z seems the logical choice, since we also believe that the E field would be pointed in the z direction as well. Okay, so remember, V doesn't have its own direction. Asking what's the direction of v is literally like asking what's the direction of water. It doesn't make sense. Or what's the direction of time? It's, well, time hopefully is unidirectional. What's the direction of mass is like what you're asking if you say what's the direction of v. So we have to derive it, we have to negate it, and we have to hat it. That's the only way to get a true full E field out of it. I'm not going to do any other components, but had there been other motions we could take, like diagonal directions, we would also need to do x and y as well. And you cannot get a magnitude until you finally get the entire E vector figured out, and then you pick out your EX, you pick out your EY, you pick out your EZ, and you do square root of E sub x squared plus E sub y squared plus E sub z squared. So you'd have to actually dissect it to that level. Fortunately for us, it's all one-dimensional here. Okay, so we're just going to DDZ this thing. We're just going to DDZ it. It's not even that hard. Okay, so we have the E field is going to be the negative of, and then we're going to have a 2k sigma. That's just kind of there to stay. And we have on the inside here a z squared plus r squared to the half minus a z to the first, right? So when we derive it, when we find the derivative, just think of z as your variable and think of capital R as literally a number. So don't even derive it. Or if you derive r squared, just think of it as 0. Okay, so you're going to put the half in the front. And then it's going to become z squared plus r squared to the negative half. Now we're going to apply the chain rule to the inside. What's the derivative of z squared plus r squared? Just 2z. Okay, that term is done. Now let's derive just z to the first. So what's the derivative with respect to z of z to the first? Just what? 1. Okay, now you'll notice something. This 2 cancels out, and we end up with this answer. The E field is 2k sigma times 1 over the square root of z squared plus r squared minus 1. And it's in the z direction. This should look familiar to you because, I don't know if you remember this or not, but before we ever did the potential of a charged disk, z units above it, we've done this formula before. You see? This formula should look familiar to you. I believe it's one that you memorized from my first test when we were back in the day when we were studying E field. And I do have a copy error right here. There's a z that I forgot to copy right to there. So this should be a z over, and that formula should look familiar. Now it looks familiar, right? Okay, straight out of chapter 23 there, see? Interesting. So that's the connection, the underlying deep connection between V and E. All right, let's try another one. So that was kind of silly because we took a potential and we derived it, negated it, and assigned it direction, and we got a E we already knew. But remember back when we did Gauss's law, E was quite hard to do. And since then, we have found that V is actually a little easier to work with. And not too many days ago, before we did our lab, we had written down the V for a charged ring. Not a charged ring. Well, we did the charged ring, but we did this complicated rod of length, a rod of charge of length L. If you look back in your notes, you'll see rod of charge of length L. And we got this horrific result. Let me see if I can write it down properly. You'll remember that whenever you have ln of m over n, you could technically split that into lmn minus ln n. Right? That might be a wise choice here, especially if we're planning on deriving this. And remember, this was all about a rod like this, right? And we were a distance a from the edge, and we were a distance y above it. So our point P is a little different arrangement from the last disk problem, where the y represents how far up we are above the rod, and a represents where above the rod we are. And it was really flexible. Like you could actually just travel anywhere along the rod and calculate the potential. It's pretty neat. Okay, so on this one, you see, we're going to have to think of left, right, up, and down. You see what I'm saying? So in this one, we were allowed to travel horizontally or vertically. There's another direction we could go, and that's around Like we could do like a little orbit around the rod if we wanted to. So like here's the rod. We could actually orbit around this way where we change theta and go around. But I don't think the E field would change anywhere as we go around that way. And I don't think the V would either, if that makes sense. You're keeping a constant R there from the charged object. So I think this is like 2 out of the 3 dimensions we could travel. We'll need to do both. So the way I'm going to do this problem is I'm not going to use X and Y. What I'm going to use is I'm going to basically DDR this thing. Do I dare? Yeah, it's basically like DDY. So Mr. Short needs to keep the V and put a Y there. Y represents like the radial distance from the charged rod. And then I'll assign a Y hat to that. This is not to be confused with up and down Y. This is like radially in toward the rod or out from the rod. And there's a negative on that. Okay, and then we also are going to have another component to the E field. If we were to go not rotationally around, but horizontally along. So if we travel like this way, you see what I'm saying? Actually, I think we would have, I'm not sure we'd even need to worry about that. As you go from one position to another, you should be the same distance from the rod. I take it back. We only need one dimension on this one. If you travel horizontally, like to the right, the potential is going to be the same. Is it? Oh, no, it's not. So that's the A direction. That's the A direction right there. So what I'm saying is there's 2 variables in this, A and Y. We're going to do basically both. We're going to do DDY, and we're also going to do DDA. And that'd be an A hat. Yeah, we need both. The potential is going to change no matter where if I adjust A or Y, the function is going to give me new values, right? So this is the answer, and unfortunately the bell's going to ring, so I'm going to stay after school and do both derivatives and put them in a vector form. So you cannot mix these. Once they are separated, they are forever separated. Okay, you cannot put them together. The only way to meaningfully put them together is to calculate, literally calculate the magnitude. So Mr. Shore is going to finish this derivative in just a few minutes, and then I'll post the video. Okay, so the bell was about to ring. So let's go ahead and finish what we were doing. So the first time I go through, I'm going to try to derive as if y is my variable and a is a constant. That's what we call dv dy. So that's this one. And then we're going to go through and treat a like the variable and y like a constant. That's called dA dv. I should have said dv dA. All right, so the first time through, here we go. This takes a bit of concentration. Let's see. I don't think I want to use the ln rules for differentiation and also the rules for square roots and quotients. So I'm just going to break this up into 2 logs. I think that'll actually be easier in the end. I can always recollapse it later. So I'm not doing any calculus yet. I'm just thinking, why don't we write this as ln numerator and this is a half power minus ln, Mr. Shore is going to use half powers, and I'm going to double check that I wrote this correctly. And I kind of double used square brackets there, so I actually haven't done this in years, but I'm going to use curly braces. Okay, let me make sure I copy that right. So I have ln of numerator. Yeah, see, I misplaced my half. I knew I was going to do something wrong with that. That's just messiness. Let me concentrate for just a second. Okay. L minus a goes here. Okay, so the square root is only on the L minus a squared plus y squared. So there's a half right there. And then the L minus a is separate. Yeah, the L minus a is separate. Okay, so that's pretty messy. All right, so the wonders of digital ink, I was able to rewrite it. and then while it was paused. Okay, so this is what I want to do. I want to use curly braces around the ln's, and then I do have large parentheses around my first log argument, inside of which I have some complicated stuff, and then I have just square brackets around my other argument of an ln. Okay, so now it's time to derive. So you probably remember that the derivative of a log is 1 over what's inside times the derivative of what's inside. In other words, you can just basically take the derivative of inside over inside. So I'm talking about the rule where you take the derivative of, let's say, derivative of, with respect to x, of ln of something. So the rule for this is just u prime over u prime over u. And it, sometimes the chain rule allows you a derivative of 1 on the inside, in which case it'd be just 1 over u. Okay, so that's the first rule you need to understand. So let's go ahead and take care of that for each of these. And then there's the chain rule as we go, so we just have to be very careful. Oh, and the first time we're doing this, we're what did I write first last time? DDYing it. So we're going to DDY, okay? So dv dy is going to be k lambda, and we're going to have 1 over, and I'm actually going to put the derivative on top, not a 1, but for now let's just do the under part. So it's going to be basically square root of L minus A squared plus Y squared plus L minus A. And then the numerator, the derivative is 1 over 2 square root of L minus A squared plus Y squared times 2Y plus L minus A. Now L minus A is, if we're going to DDY, L minus A is going to be treated as a single value, so you're not going to actually even worry about it. So the only thing that got treated as a variable when I was working is this little y squared right here. That's how I got the 2y on top. Okay, so that was just basically in the rule of ln u. The top here is u prime. This whole numerator is u prime, and this is just u. So I had to use the chain rule also to get u prime. Okay, so that's the top minus, and then the second one, it should be the denominator, square root of a squared plus y squared minus a. And then in the top, the derivative of the inside. Since y is the only variable on the whole problem, the y squared is the only thing I have to worry about. So it's going to be 1/2 a squared plus y squared to the negative half, blah, blah, blah. And it's going to end up being like this. Very similar to last time. It's 2 square root a squared plus y squared. Then the derivative of y squared, which is 2y. And then there's a minus a just chilling here at the end. But he's derivative 0 as far as y is concerned. Wow, so that's really messy. Really, really messy. But that's kind of what it looks like. Okay, you'll notice a couple things cancel out. So like the 2 cancels with the 2 here and here. And you could use a common denominator to recollapse it. But I'm not really excited about that idea. So I'm just going to kind of leave them separate. So the E field in the Y direction, to get the E field, you would put a negative on here and also a Y hat on here. So it's going to equal negative K lambda times all this garbage and a Y hat at the end. Okay, by the way, I should have probably mentioned this earlier, but since Y is the distance from the actual rod, and it's a radial measure, in the world of cylindrical coordinates, we usually actually call that r. So, okay. All right, I'm going to go in and just erase the little 2's that I canceled and kind of clean this up a little, just so you can see it better. That numerator is just plain y. small eraser. There we go. And then this 2 canceled with this 2. Okay, if you want to, you could make this simpler by just letting, you know, L minus A be called like B or something. And then you could let, when you rewrite this, it looks a little cleaner. If that makes sense. It looks a little cleaner. Okay? Notice there are no logs in this E field. Okay? All right, that's not the whole E field. That's only the Y component of the E field. Right? That's the Y component of the E field. Okay, now we need to do the A component of the E field. The A means you're going to travel left and right, and you have to admit, as you travel left and right, the field does change, and it's because of the edge effect on this cylindrical rod. Okay, so you cannot expect the same V with different A's because the original function V at the top of the board right now has A's in it. So that means if you change A, you change your potential. It is A dependent and it is Y dependent. So now it's time to find E sub A in the A direction. And that's going to be negative dV dA, A hat. In other words, negative K lambda times. And we're going to do the same calculation this time, but we're going to treat the A as our variable and the Y as a constant. So the good news is it doesn't appear too different in our work, like when we're actually working. Okay, so Mr. Shore does not need the E sub Y right now, so I'm just going to grab it and group it and shrink it real small. We just don't want it to be in our face right now. We can enlarge it again later. We're focusing on a different component of the E field now in the large. Okay, here we go. So first of all, it's an ln, so it's going to be something over the inside. See, if we were using b instead of L minus A, that would just be b squared plus y squared. It'd look a little nicer. And then it would just be plus b instead of plus L minus A. Okay, and then the second one's going to have that. Okay, the derivative is the derivative of the inside of the logs with respect to A as a variable. So imagine if A was your variable. So you got to pay close attention because there's a there and there's an A there, right? Okay, so first thing you do is you take the derivative of the top part and you get, or the derivative of the inside part, and you get 1 over 2 square root of L minus A squared plus Y squared. Then you do plus negative 1. The negative 1 is just the derivative of the L minus A. The L is 0, and then the negative A has derivative negative 1 if you're DDAing, right? If you're doing a DDA. So it's kind of complicated. This is a minus 1 right here. Okay, and then I also need to do the derivative of the inside of the radical, and that goes above the radical. So I'm using the rule that if you're doing the square root of u, right, and you're trying to ddx that thing, you end up with basically 1 over 2 rad u and then times u prime. So it's u prime over 2 rad u. So there's an ln going on, but there's also this derivative of the inside of the radical over 2 times the radical of the inside. All right, so almost done here. It looks like this is going to be, the derivative of that's going to be 2 times L minus A to the first times negative 1 plus 0. That's the derivative of L minus A squared plus Y squared. So that's just basically, I think it just comes out to be negative 2 times L minus A. It's pretty simple. Negative 2 times L minus A. And that is that. All right, so this is kind of complicated, but I'm going to highlight a couple little things here, and then I'll erase it. This is the inside of the log. This is the derivative of the inside of the log. To get the derivative of the inside of the log, we had to think of this as a square root. So this is the 2 rad u on the bottom, and here's the u prime, the derivative of the inside of the radical. Pretty complicated. All right, the next one's a little easier, not too much. But we basically have 1 over 2 square root of a squared plus y squared times 2a. 2a is the derivative of the inside of the square root. And I think I just erased something by accident. Yeah. Okay, then we have a minus a there. That's just going to be minus 1. Okay, again, the 2's cancel top and bottom. So I'm talking about this 2 right here, and this 2, this 2, and this 2. Right? Those 2's cancel out. All right. Okay, so canceling those, I'll just erase them. Gotta be real careful here, huh? There's a lot going on. All right. To have a negative of L minus A is the same thing as having A minus L. So I'm going to switch that around just to make it look a little nicer. And that looks a little nicer. Not too much. Okay. And that's the A component. And so we need to put an A hat on it. So now you can see why we wanted to stay away from doing field of something like this that's finite and where we have the flexibility to move in multiple directions. We stayed away from that earlier. All of our E-field problems were kind of oversimplified, and Gauss's law helped, but it was not the final, solution. And as you can see, this whole thing is your E-field. In 2 components. I was going to draw a box around it, not highlight it. There we go. This is our E field in 2 components. Now, let's say you pick a point, A units along the rod, Y units above the rod. You plug those numbers in, you're going to get a Y component of the E field given by the first equation and an A component of the E field given by the second equation. So let's say you get 2 newtons per coulomb, 4 newtons per coulomb. You could just basically set up the magnitude calculation. You could say, look, my field is 2, 4, I think I said 4, 2, or whatever it was. And then you could basically find the magnitude. So the square root of 2 squared plus 4 squared is root 20. 4.5 newtons per coulomb. You see what I'm saying? When you write vectors, I've always liked this format myself. But you have to be kind of careful with it because people are going to assume this means X and this means Y, right? This means X and this means Y. So that's one of the reasons why physicists, because they use multi-coordinate systems, sometimes they're a little reluctant to use the braces, I think. So they would rather say, look, they wouldn't write this. They would say, look, the best way to write the field is using the unit vector component form. So they'd say, look, it's 2 newtons per coulomb in the y hat direction and another 4 newtons per coulomb in the a direction. You see what I'm saying? Also, one last closing comment on this issue. When we were doing this problem kind of 2-dimensionally, we weren't really thinking about cylindrical coordinates, but I think I kind of need you to think about this here. If you pick a point that's yay units away from the rod, right? Certain number of units away from the rod. Normally, it'd probably make more sense to call this R than to call it Y, right? Okay, so that would be called like R. And then as you go left and right along the rod, so as you move over to new locations, that might be kind of like the idea if you had a cylinder with a z-axis through it. Some of you took my calc class last year, so you know what I'm talking about. Moving along the axis of the cylinder in the direction parallel to the axis of the cylinder has always in cylindrical world been called the z direction. So z hat would be this way, r hat would be radially outward. like that. So it might make more sense. I know that this is not how we did the problem, but it might make more sense instead of calling this y to actually call this r hat. It means, you know, from the charged rod, that component is pointing radially out from the charged rod. So r hat points radially out, normal to the surface of the cylinder. See? And then instead of calling it a hat, anytime you move along a cylinder, physicists like to call that z hat actually. So it'd be kind of a quick little change of things at the end. Normally when we're doing r and theta, we also want to consider the idea of wrapping around in a circle. So you would also want a theta hat here. But here's the thing about theta hat. If you go back to the original drawing, right, you'll notice that, and I'm kind of erasing the original drawing. I don't know why. Just don't like, it's just so messy. Here is your original rod, and if you pick a point further from the rod, so if r is changed, you're going to experience different field. If you pick a different point along the rod, we're calling that z now. So if you take your point like this and you scoot it over to here, you're going to experience a different field. See what I'm saying? And that's because the field is varying because of the edges of our rod. If this was an infinite rod, we wouldn't have any variation as we move along the z, right? And we were calling that a before. So in other words, y is like the r and z, a is like the z. And so the third direction you could travel is you could just kind of go in orbit around the rod. So you could just take your point and kind of say, okay, well, I was at this angle. Now let's come over to this angle. Let's go over to this angle and kind of go around the rod like this. Some points in the back there. So this ring is centered on the axis of the rod. So if you go around that way, and it's supposed to look like it went behind the rod. Maybe I should have just left this all blue right here. Let me redraw this a little bit. I just want you to understand cylindrical ideas here too. Okay, as you go around that direction, that's called theta hat. Okay, and you'll notice something. The field's not going to change. Neither is the potential, actually. And that's why in the original problem, there is no hint of a theta anywhere. Like there's only a's and y's. There's no hint of any thetas anywhere. So, I mean, you're welcome to dd theta this thing, but you're literally going to get 0. So when you negative dd theta, so when you find the e sub theta, right? Oh, man, this marker's hard to write with. When you find e sub theta, you do it by doing negative dd theta of v, and you attach a theta hat. Since there were no thetas in v, you literally get 0 newtons per coulomb theta hat. So the complete field in cylindrical coordinates looks like this. You see? The complete field, as our final answer is 0 newtons per coulomb in the theta direction, plus, and then I'm just assuming these are 2 and 4, I kind of made up those numbers, 2 newtons per coulomb in the r direction, and 4 newtons per coulomb in the z direction. So you can see why physicists probably would not want to use, you know, like 024. Somebody would just assume that those are x, y, and z. Also, we usually do it in the order r, theta, z anyway, so we would want to switch the 2 and the 0 around. So if you write it up here where I'm putting the green star, if you write it this way, no one's going to be confused. But if you try to write it like this, people are going to get lost. So, all right, so that's how you go from potential to field. Notice this can be done with any scalar field. You can always derive it in every dimension and attach the negative and the y hat, and out pops a meaningful field, but it's a vector field, and this is responsible for forces, as you know. So now you could just times by q if you have a test charge q and actually find the actual force, which then of course leads to acceleration. And once you have acceleration, you start getting kinematics involved. Keep in mind that when we do have small particles, following under these powerful forces of kinematics, powerful dynamical forces, the kinematics are going to cause very, very high rates of movement. So you will have to use relativistic kinematics. If you stick an electron anywhere near this thing, it's going to take off. You could have particles that get close to the speed of light if there's a very large field and a very tiny, tiny light particle. So that's it.